the most mysterious and challenging elements containing various celestial drawings in the universe are undoubtedly black holes. In our video, we will try to examine and understand black holes from a scientific perspective. Here's our new video: Mysterious Elements of Space, Black Holes. It is believed that the universe may also host white holes, a hypothesis that has not been conclusively proven and shares similarities with black holes. Before delving into the mathematical aspects of black holes, let's recall what they are. Black holes are regions in the universe where matter and energy are densely compressed, making escape impossible. Understanding the creation of a black hole requires delving into complex mathematics. Nevertheless, they are real entities in the universe predicted by Einstein's general theory of relativity, and indeed discovered in recent years. In 2019, for the first time in human history, a black hole was photographed and published. Black holes are formed as a result of the supernova explosion of stars much more massive than our Sun. So, what is a white hole? Considering the many entities waiting to be discovered in the universe, could white holes be one of them? When examining black holes, it is possible that white holes may merge if we assume there is no mass at the event horizon, or perhaps white holes are singularities of a black hole that exists without mass. Before moving on to white holes, let's take a closer look at black holes. A black hole is a cosmic entity in astrophysics that is so powerful due to gravity that it does not allow any form of matter or energy to escape from itself. Black holes are regions where matter is consciously gathered to a point in space. It is estimated that time slows down or stops inside black holes. Black holes are based on Einstein's general theory of relativity, although direct observation is not possible. Indirect observation techniques using various wavelengths have led to the discovery of black holes. Today, the existence of black holes has been almost universally confirmed and established by astrophysicists and theoretical physicists. A black hole is a mass calculation concentrated at a point due to gravitational singularity. This mass shapes a sphere centered on the singularity, forming the event horizon. This sphere can also be considered as a region in space covered by the black hole. When it comes to stars, a black hole does not cause any changes in terms of gravitational force on another cosmic object with the same mass. In other words, black holes can be considered as cosmic absorbers exerting an irresistible gravitational force. For example, if there were a black hole with the same mass as the Sun instead of the Sun, there would be no change in the orbits of the planets in the solar system. There can be various types of black holes in the universe. The type of black hole formed as a result of the gravitational collapse of stars incapable of exerting gravity on itself is called a stellar black hole. These black holes can be found at the centers of galaxies and can reach massive masses of several billion solar masses, known as supermassive black holes. Additionally, there may be intermediate mass black holes with mass between these two types. The smallest mass black holes are believed to have formed during the Big Bang at the beginning of the universe, and they are called primordial black holes. However, the existence of primordial black holes cannot be directly observed because black holes are structures that can even absorb light. The presence of black holes is understood through gravitational effects of surrounding objects, especially microquasars and active galactic nuclei, where matter falling onto the black hole heats up and emits light powerfully. These observations demonstrate that objects conforming to the general theory of relativity are exclusively black holes. The concept of black holes first emerged in the 18th century within the framework of Newton's law of universal gravitation. However, at that time, it was not possible to know, for example, whether massive objects with an escape velocity greater than the speed of light existed. Therefore, the concept of black holes remained a fantastical idea until the early 20th century, particularly with the introduction of Albert Einstein's general theory of relativity. Black holes are astrophysical objects, and their direct observation is very challenging. The physical properties of their central regions cannot be precisely defined. The gravitational singularity in their central region has not yet been explained with the quantum gravity theory. Additionally, defining black holes with a wide range of parameters is a complex process. The definitions of black holes in our universe are based on only three parameters: mass, electrical charge, and angular momentum. If a black hole is rotating, it drags the surrounding space-time with it. A rotating black hole shapes the dynamics of the space-time around it, having an oval shape that extends up to the event horizon touching the poles. A particle within these boundaries is forced to rotate due to the dragging of space-time, and this process is known as the Penrose process. The region considered as a mesh where light and matter can no longer escape is called the event horizon. We cannot know what lies beyond the event horizon because it is a space that cannot be understood through physical examination. The laws of knowing what is beyond the event horizon cannot be explained, and there is no way to acquire information about it. The state before the event horizon is proportional to the current state. For example, when a star with a mass equivalent to 10 suns collapses inward and becomes a black hole, the diameter of the event horizon can rapidly reach up to 60 kilometers. As a black hole consumes matter, expands the event horizon. With the expansion of the event horizon, the gravitational force also increases. Theoretically, time stops at the event horizon of black holes. In some black holes, the existence of two event horizons is possible. In the center of a black hole, there is a region where the gravitational field and space-time images come to an end, called the gravitational singularity. However, the general theory of relativity cannot define this region where space-time is infinite, and it is uncertain regarding gravitational singularities. The general theory of relativity does not generally take into account the effects of mass gravity. When space-time is infinite, it may be subject to quantum effects. As a result, a theory that can accurately define gravitational singularities may be a mass gravity theory that takes all quantum effects into account. However, for now, accurately defining gravitational singularities is not possible. Nevertheless, the fact that matter entering black holes cannot escape and the gravitational effects hold it inside indicates that gravitational effects retain mass gravity. The existence of black holes is not only a result of the general theory of relativity. Other mass gravity theories also consider the possibility of black holes and predict that they are formed by matter compressed in a region of space. For instance, if our sun were compressed into a tower, it could become a black hole. In astrophysics, a black hole is considered the final stage of the core's collapse. Toward the end of the evolutionary processes of stars, the compression of matter can result in two types of black holes: accretion black holes or neutron stars. Accretion black holes are found in a state where they balance the compression pressure of electrons, while this effect is not present in neutron stars. When a star in its evolutionary process reaches the critical mass point and the gravitational force is large enough to overcome pressure effects, a black hole can form. In this case, no known force can maintain equilibrium and the object collapses. Black hole formation can also occur through other means, such as adding or merging matter from another star into the core of a star. However, these situations are quite rare. Most known black holes in the universe have been formed by matter compressed in space, as predicted by the general theory of relativity and other mass gravity theories. These theories not only predict the existence of black holes, but also explain their evolution. As a result, scientific findings support the likelihood of the existence of black holes in the universe, and there is a general consensus among different mass gravity theories. However, the complete properties and internal structure of black holes are still not fully understood. One of the initial methods for finding a black hole is to examine binary star systems to determine the masses of the binary stars, if one star is not visible from the other. It has been thought that the less massive star could generally be interpreted as a neutron star or black hole, if the observed tilt angle of the star is also known. It is examined whether the gravitational force of its companion exceeds the maximum mass limit of neutron stars. If it exceeds the limit, it may indicate a black hole. Otherwise, it could be a white dwarf. Another observation method involves the information that some stellar black holes become apparent when they emit X rays during the accretion of matter. Such black holes typically form as a result of a massive star's supernova explosion. Another phenomenon indicating the presence of black holes is observed in flows, particularly in radio wave observations. These flows arise from large scale changes in the magnetic field around the black hole. The small sizes of black holes make direct observations challenging. For example, directly observing black holes with diameters of a few kilometers is almost impossible. A black hole that is observable has the mass of the Sun and is at a distance of approximately 1 parsec, about 3.26 light years, will have an angle so small that observation is nearly impossible. This demonstrates a situation where observation is almost impossible. However, the position of interacting black holes may be more suitable for direct observation. The flows around a black hole are proportional to its mass. For instance, the mass at the center of a black hole is an average of 21.6 million solar masses. This is indeed a colossal size, but considering the infinity of the universe, it still corresponds to a small region. Currently, devices working in millimeter ranges and high-resolution telescopes are used in the examination of flows around black holes. With this technique, obtaining images of black holes becomes possible without being just a fantasy. An image obtained with this technique of the black hole at the center of the M87 galaxy could be a promising step for future observations. Discovered in 1965. Cygnus X1 became the first known astrophysical system containing a black hole. This involves the transfer of matter from a normal star to a black hole when a black hole is part of a binary star system. Within the black hole, a disk forms due to the conservation of angular momentum. This disk reaches very high temperatures near the black hole's massive gravitational potential, allowing the detection of the black hole. Binary star systems containing a black hole or a neutron star that creates interstellar flows are called terrestrial parents. These flows have been observed in a second system with controversial radiology, Euro G16-55. However, the debate continues because there's evidence that the flows in the system are not faster than light. Quasars, discovered in the 1960s, first identified massive black hole candidates with active galactic nuclei in the efforts of radio astronomers. The most significant evidence for the existence of massive black holes is observations of the orbits of stars at the center of our galaxy. The orbital velocities of these stars show that no cosmic object other than a black hole can be found around this characteristic center. Following this discovery, black holes have been detected in other galaxies. In November 2014, a group of astronomers announced the discovery of a triple black hole in our galaxy. The star cluster is the remnant of a star cluster composed of large stars that has been consumed and shattered by the central black hole. This observation supports how stars and other black holes around massive black holes grow as they consume. In June 2004, astronomers discovered a massive black hole called Quasar 9069-30 at the center of a galaxy 12 billion light-years away. They found that this massive potato-shaped black hole gathered the total mass of these stars. Considering the Big Bang, this observation shows that the formation rates of massive black holes in galaxies are a visible phenomenon. One of the fundamental issues regarding black holes is the question of under what conditions they form. Initially, it was thought that the formation conditions of black holes were very specific, and they were considered rare occurrences in the universe. However, the work of Stephen Hawking and Roger Penrose mathematically demonstrated that such formations are possible, and black holes emerged before observations confirming their existence were made in the early 1970s. Subsequent observations confirmed that black holes are indeed objects frequently found in the universe. At the center of a black hole, there are gravitational singularities. This singularity is concealed by the event horizon and various types of black holes. Presently, physics cannot precisely define gravitational singularity. However, this is not of great importance because the gravitational singularity remains confined within the event horizon and does not influence external events. However, if there is a singularity not constrained by the event horizon, mathematical solutions exist. In this case, one can no longer speak of a black hole, but a naked singularity can be discussed. However, studying naked singularities is extremely difficult in terms of parameters because understanding the singularity environment is not possible. Even today, not much can be said about naked singularities, at least until the 1990s. In 1971, British physicist Stephen Hawking showed that the surface area of the event horizon never decreases, regardless of the type of black hole. Jacob Bekenstein suggested that black holes have entropy proportional to the surface area. Although it has not been directly verified, this has provided insights into various similarity relationships in thermodynamics and entropy for black holes and may aid in understanding quantum gravity theory. Black holes are intriguing because they are the most stable and longest-lived objects in the universe. They lose energy very slowly due to their mission. However, technology that can harness this radiation is not yet available. In 1974, Stephen Hawking's quantum theory, applied to space-time in general relativity, discovered that black holes actually emit radiation, now known as Hawking radiation. Therefore, black holes not only absorb radiation, but can also emit something. However, according to our current knowledge, black holes cannot emit any other radiation because the escape velocity on their surfaces is higher than the speed of light. If we could place a flashlight on the surface of a black hole and try to pull it back to the black hole's surface due to the gravitational effect, this effort would not be successful. The variability of entropy near the event horizon is considered more satisfying than the variability of light isomet falling into the black hole in terms of matter and energy entropy. Nevertheless, many issues remain unresolved, especially regarding quantum aspects. General relativity shows that black holes in the universe are somehow always interacting with each other. Corridors connecting black holes in this structure resemble a path you set up inside a house. These corridors connecting black holes are called a wormhole, or in other words, Einstein-Rosen bridges. Black holes can open into another universe, or the transition to this second universe may be closed. These corridors associated with black holes are called wormholes or wormholes. Assuming that there are many black holes in the universe, research continues on these structures. Dear viewers, today we embarked on a journey to explore and understand the mysterious and captivating phenomena of black holes in the universe. They are among the most enigmatic structures in the cosmos. The theory of general relativity has helped us comprehend how black holes exert their influence on space-time through gravity. However, the exact formation and behavior of these dark entities still pose many questions. Horizon Entropy seems to offer a new perspective on understanding the entropic properties of black holes. Ongoing research that seeks to unravel the puzzle between quantum mechanics and general relativity may help us better grasp the mysterious nature of these entities and perhaps define their role in the universe more clearly. As far as we know today, it is assumed that there are many black holes in our universe. However, scientists continuously conduct observations and theoretical studies to delve deeper into this assumption and understand it better. Perhaps in the future, we will gain a clearer understanding of the nature of these mysterious formations and their role in our universe. I appreciate your company throughout this adventure. As long as our desire for exploration and learning persists, we will continue unraveling the secrets of the universe. Thank you for joining me on this journey. Enjoy the exploration.